Hello everybody, do you like AI, artificial intelligence? Now everybody speaks about it, but I want to make it clear, if you like AI because it makes your life simpler, or you want to put AI on your CV to ask for a salary raise, sorry, this is not the video for you. In this video, we start from the need of AI, so to optimize the code, because artificial intelligence is very heavy, computational intensive for computers, so we need highly optimized algorithms. And for many of them, we have actually many functions that we need to optimize. Now, in the optimization process, we need to compute the derivatives of them. Of course, this doesn't happen only in artificial intelligence, can happen also in machine learning or generic high-dimensional optimization problems that might come, I don't know, in portfolio optimization in finance or might come in some engineering. There is so many stuff out there. So let's talk about it. And I promise you, while understanding how to make differentiation in a very efficient way, we will learn a lot of interesting tricks, okay? Now, in a previous video, I discussed the fact that if you just adopt, let's say, the standard definition to compute derivatives, you're going to end up in serious issues. You can watch it if you are interested. So, if you apply the standard definition, you're going to fail. Now, what can we do? Over time, they did some studies, and let's say mathematicians and computer scientists, they came together and found out a way, actually more than one way, to solve this issue in a very elegant way without putting necessarily any kind of approximation. Okay, so now we have some algorithm that can be used for any high-dimensional optimization problem. Let's say this is the general topic. In this video, I'm going to speak about, let's say, 3 solutions. The first is the symbolic manipulation. I will go quickly through it because it's very nice, but it's not really efficient. And then I'm going to speak properly about automatic differentiation that we can divide, let's say, in 2 categories, the forward and the reverse automatic differentiation. Now, while speaking about this first point, we are going to learn a lot of tricks that I find personally very interesting. But of course, if you are not so interested in the theoretical part, I will split the video in sections so you can just jump to the practical part where I will try to make it so easy that you can literally do paper and pen. Because, in my opinion, if you want to learn how to make this kind of stuff, you have to be able to do paper and pen. Only when you're able to do this, then you can go back and make it, some algorithm. So, I will try to make exactly an exercise that I expect you to take paper and pen and repeat by yourself, if you really want to learn. But another very important reason I make this video is because I've seen online already many videos that describe the automatic differentiation, but they don't let you really understand. They stay more theoretical, so I really want to go practical. That's for me very important. Even though the large part will be, let's say, theoretical, I'm really focusing on the practical part. So let's start first of all with the symbolic calculus. I will show you some basic example by using Python. I use Python because, it's free and simple to use. There are much better tools around, but, they are under license. Anyways, let's just understand what I mean by symbolic calculus if you have never been there. So here you have an example. You just import a library that is called SymPy, for example. And in this library, you can just define symbols. So you say x and y for me are not variables, are not numbers, are symbols. So then you can tell, okay, given those are symbols, if you like variables, you can just use them to do computation. So for example, you say, I want to compute the differential of the sine function with respect to the symbol, or if you like, the variable x. And the output is going to be cosine. So this library basically implements all, let's say, the rules you would use at school to compute derivatives, exactly like the derivative of sine is cosine. Of course, you can do much more than this. I mean, this is trivial. So, for example, you can define a function, right, that in this case is the multiplication, the product of 3 components. Each component is not trivial, like I have sine of cosine of x squared, or I have log of tangent, or I have exponential of x times square root of 1 plus x, right? This is absolutely not trivial function, okay? And you can tell, can you compute me the derivative? Boom, here you got it, right? So symbolic manipulation is exactly the exercise you will do at school. and is very nice. Now, there is one problem, is that it's slow. Okay, if you try to implement this, of course the algorithm itself is not simple, so will be slow, but itself the derivatives are not friendly. Let's just look at this page. I define a function of one simple line, okay, and you end up, when you compute the derivative, having, let's say, 3 lines roughly. Let's say, to make this example more extreme, let's make the second derivative, the derivative of the derivative. And if you see, we started from a function of 1 line, first derivative 3 lines, second derivative is already half a page. Now, if you go the third derivative, surprise, surprise, I have problems fitting it into one single page. So the tool is very nice, but the derivatives are intrinsically making our life harder. This is not because our math is unfriendly. The derivative is unfriendly. I know you think at school computing integrals was difficult, making derivatives but this is somehow misleading. The reality is very different. Let me give you an example. First of all, let's look at the rules, for example, here in Wikipedia. If you start, for example, with a product of 2 functions, okay, when you compute the derivative, you double, let's say, the number of terms, because you have the first derivative times g, f prime, for example, plus f g prime. The same when you make the fraction, okay, you have a fraction, you want to compute the derivative, you end up in a fraction that is less nice, let's say, at least at first glance. But statistically speaking, when you take a random function, you're gonna get, let's say, less friendly stuff. The same happen, of course, if you have a composition rule. H function of g, function of x. When you compute the derivative, you have h prime of g times g prime. Okay, let's look at this more in an intuitive way. Let's start with the Dirac delta distribution. Dirac delta distribution is such an unfriendly object that is not even a function, it's a distribution. And the reason is that you have one point where it kind of goes to infinity. Okay. Now, if you compute the integral, you end up with the step function. The step function is a function. Okay, it's not continuous, you have a jump, but never goes to infinity. Okay, so it's already more friendly. Now, if you compute another integral, what you get? You get basically 2 lines, they have a cusp. Okay, cusp is an angle basically in one point, but now you have something more friendly because the function is continuous. So we are getting something nicer. If you compute another integral, what you get? You get basically a function that on one side is flat, the other is a parabola, but now this function not only is continuous, but is also smooth. So every integration you make the function more friendly. But in the other direction, every time you calculate a derivative, you make the function less friendly. So this is intrinsic, let's say, genetical problem of this. Okay, so the symbolic calculus, even though we can implement it, is most of the times not so friendly as we would like. Now, let's make it more efficient techniques. And I want to make it clear. First point, they don't introduce any approximation. It's not like when you make the numerical differentiation. In principle, those techniques are perfect. The second point I want to make, and that's very important, is that in many places you will find that the forward accumulation, so the first technique, is using, let's say, repeated rule of the chain derivative, partial derivative, starting, let's say, from the external function going into the internal, while the reverse accumulation is doing it in the opposite direction. For me, this is really misleading, okay? So please cancel it from your mind. I know most of the videos that maybe will be even suggested by YouTube next to this video, most of the video, they go in this way. But for me, you really miss one important point. Those two techniques are completely different, okay? So the first technique is based on the mathematics of dual numbers. Now, I will explain these dual numbers are very simple, okay? It will take a bit of time to get familiar, but once you understand them, they are so friendly and so easy, okay? There is nothing complicated there. The second, so the reverse accumulation technique, is based, let's say, on some kind of recursive algorithm, not really explicit. It's more somehow creating a computational tree or computational graph and then going step by step through it. But the logic is so different that I call these two techniques independent. Those are two completely independent techniques, okay? Now, let's jump into the first one, forward accumulation. The forward accumulation is let's say, connected to the dual numbers. But the idea that is at the origin is more related to the Taylor expansion. So, let's look at the Taylor expansion. Let's say you have this function that I'm showing you here, exponential of x times sine of x. And I ask you to compute the Taylor expansion. Now, you would need to compute all the derivatives of this function. If you remember, now I'm using, let's say, a simplified notation where I omit a bit of the dependencies in the variables to make it more readable. But anyway, the Taylor expansion is something like a polynomial where you have the function computed in a specific point, like 0, plus the derivative times x, plus the second derivative times x squared divided 2, plus in principle infinite terms. Okay, now if you want to compute the Taylor expansion of this function, you should compute all the derivatives. And I mean, there was a crazy professor in my university asking at the exam to make the Taylor expansion to order 15. Okay, you saw in the previous example at the order 3 how unfriendly it can be. Think how crazy was this professor. If I would have knew back then, I would use a completely different approach. Let's look at it. First of all, we already know the Taylor expansion of this function. This is written in any book, okay? So if you don't remember, I just reported here that the exponential is 1 plus x squared over 2 plus x3 over 3 factorial and so on and so forth. The sign, you have only half of the terms with alternate sign. Okay, we already know this. Why not just we multiply them, okay? And what do we get? You know, I just multiply the two polynomia, truncating. Let's say I'm interested in the first 3 terms. I will just write the first 3 terms. Those are two polynomia. I can just multiply them. Very easy. And actually, this is even easier than an usual polynomial multiplication because I'm going to ignore any term that is order x to the 4th power or higher. Okay, so I'm going to end up only with 3 terms, trash everything else. I didn't compute any derivative. I have the Taylor expansion. This is a brilliant, genius idea. So simple, so efficient. Okay. Now, when I wrote this, if I want, I can read back all the derivatives of this function because they are already written there implicitly from the Taylor expansion. So the first derivative is equal to 1 because it's just the term in front of the first, x to the first power is multiplying 1. Then you have x squared divided 2, that is multiplying 1. So the second derivative is 1. X to the third power divided 3 should be divided 6, so we need to multiply by 2. So the third derivative is just 2. Okay, we can compute the derivatives by just using what we already know and applying, very simple polynomial multiplication. So why not making this technology ready to be used to compute derivatives in a way more, targeted way? Of course we can. So this is what we do. I mean, we can define some dual numbers. Those dual numbers, you can think them like vectors of dimension 2. So a dual number is just a couple of numbers, okay, that we store together somewhere in our memory. I will just use this notation with the brackets like kind of V-shaped to remember that it's not a vector, so there are some differences, but not so big, so it's pretty convenient to use this kind of brackets. So let's say you have a Taylor expansion of the exponential function, and you want to compute now in a generic point x0. Before I was setting around 0, so let's say the Taylor expansion in 0, now in a generic point x0. So here I'm writing you the Taylor expansion. You have exp to x0 plus x0 times x minus x0. That's the how much you move away from x0, and then higher orders. And I can just read the value of the function in that point, and the first derivative, they are here, exp of x0. So let's say x0 is equal 3. Okay, here I should have put x0, but anyways. So then our dual will be e to the third power for both coefficients. That's like 20.09. Okay, we can do this for any function. Let's say I take the sign. Okay, the sign as a first term is sine of x0, the second term is cosine. Fine. Let's put them into our dual number. And let's say we still stay in 3. Now we need the sine of 3, cosine of 3, 0.14 minus 0.99. I'm just want to tell you that we transform any function into a couple of numbers. Okay, so simple. Now, of course, we can make a general formula where, remember, the first term is, let's say, we call finite part, is the function evaluating the point we are interested in. The second part is the derivative, or if you like, the infinitesimal part of this function. Okay, sometimes you call it, if you see in the literature or in the videos around, they call it the infinitesimal part, the second one. Okay, fine. Now, let's consider a special case. Let's see if you understood what I explained. What is x, the dual of x? A variable x, yes, but x is also a function. So can we make the dual? Yes. And actually, we have to do it. If you have an idea, just try to do it, pause the video, think about it. Otherwise, I will tell you right now the solution. So what we do, x is a function. We can compute the first derivative, that is 1. Okay, derivative of x over x is 1. So we can rewrite the Taylor expansion of a variable, if you like, as x0 plus 1 times x minus x0. Okay, this is just the Taylor expansion, and if you think of it so simple, because we have x0 minus x0, so they cancel out and you have x equal to x. But then, thanks to this, we can read the first term of the dual as x0, so the point where we want to evaluate the function, and the second term, so the infinitesimal, is just 1. Okay? Any variable is going to be substituted by the value where we want to compute the function and 1. What about the constants? Can you do it? Feel free to pause the video if you need to think. Here is the solution. You just make the same Taylor expansion, but the derivative of a constant is 0. So we have the constant is the value itself 0. Okay, so any function, we take the value of the function and the first derivative. Constant is constant 0, variable is variable 1. Okay, those are the basic rules to start with. Now let's go to a more complicated case. What is a function that is reading as an input now a dual number? Okay, this question we can reply by using the chain rule derivative. So let's first introduce, let's say, a second function, let's call g, okay, where the dual, as I just said, is g in x0 and first derivative in x0. Let me call these two stuff a and b to make it clear to you. Those are just two numbers. I call a and b to make it super obvious to you that we are just stirring a vector of numbers. Okay, any function, boom, two numbers immediately. Now, what is the function that is reading two numbers? Well, we can take the function f of g, where g will be a dual, but for now we just make the Taylor expansion as usual. If you try, you will see that this is the first term, and the second term, so the first derivative, is just the chain rule, right? F prime in g times g prime, okay? So this first term is going to be the first in the dual, and the second term, this derivative, will be the second term in the dual. So let's substitute everything, and you have that a function that is taking g of x, let me write a and b, okay? So function of a and b is exactly function of g of x. It's going to return what? The function in g, but g is a, so the function in a, and as a second term, the derivative in a, because read the Taylor expansion is f in x of g of x, 0, times the derivative of g, so b. Okay, we find out the way to take any function, feed the function as an input with a dual number, and get a dual as an output. We can take as an example, just to understand. If you have a sign that is taking as an input the dual 3, 2, then what you get as an output? The sign of the first, so sign of 3, and the second term is going to be 2, the second term in input, times the derivative of sine, so cosine in 3. Okay, this is an example of what I mean, of a function taking as an input dual and output a dual. Well done. Now that we understood how to deal with functions, let's do the basic arithmetics. Okay, so if I give you two duals, okay, can we compute the sum and the product? Well, we take two functions, we just make the Taylor expansion, we write them as duals. Now should be super clear, okay? If we want to compute the sum, let's just sum the two Taylor expansions, right? And you will end up that you sum the finite parts and you sum the first derivative. So the sum of two duals is just the sum component-wise. This is exactly the same rule that you have for vectors. We are not getting that far, okay? I could compute now the difference. Come on, it's trivial. Let's just go straight to the product. If you have the product, you take the two Taylor expansions, you just multiply, those are two polynomials, you multiply everything, ignore any term x squared or up, of course. So what do you get? Well, the product of two duals in the first component, I did a mistake, is f times g, sorry for this typo. The second component is the cross product, okay? fxg plus f in gx. Very simple. Okay, it's not exactly the same as when you make the product of two vectors, otherwise we could call this vector. It's the dual, we have a slightly different rule. So we end up building an entire algebra, an entire set of rules to deal with these generalized numbers that we call duals. So constant becomes C0, x variable becomes x1, then you have the sum and the subtraction. That's simple. The product we just proved. Here I put it in a right way, the formula, likely. You can do also the division, right, the fraction. You can take it as an exercise. Can you prove it? I mean, if you think of the second term, is just, if you look at the derivative, the rule of the derivative of a fraction. So somehow, if you play around, anyway, you can just try or you can find probably online the solution. Then we have the rule, if you have a function of a dual, returning a dual. I make the example of the sign. Why I make this example? Because if you are doing implementation in a computer, whatever, library, I would suggest that maybe it's better to explicitly implement all the functions you use very often. Most probably, you're going to end up with a code that is faster. So I would explicitly implement the rule for sine, cosine, exponential, tangent, whatever, logarithm, and so on and so forth. Okay, and then you can implement the general rule like, as a reserve. When it doesn't go one that you already know, okay, you go for that rule. That's my advice. Of course, feel free. Of course, then there is also the rule of the power, so AB to n power k, that is, as well, you can try to do this as an exercise. Okay, we have our algebra. We are almost ready to go for an example. But before going to the example, I really want to make it clear for you that vectors and duals are somehow the same stuff. Actually, also the complex numbers. In principle, I could also make the polynomial and other stuff, but let's stop just for these three examples. So here I make a table. Let's say you have two vectors with components a, alpha, b, and beta, or you have two complex numbers, a plus I alpha, b plus I beta, or two dual numbers, that is like the vectors. Okay, so in all these cases, you basically have four real numbers as an input of the problem. They are just stored in a slightly different way. If you want to compute the sum or the subtraction, it's super easy. And basically you have the same formula. You just return the output slightly in a different way, organized in a different way, but essentially it's the same. When you make the product, okay, for the vector there is different kind of products. You have the scalar product, the external product, blah, blah. If you make the simple scalar product, you are going to return IA times B plus alpha times beta. So this is going to be a single real as a return of the function. When you have the complex numbers, instead you need to return the real part and the imaginary part. They are just computed with these rules. The cross product with the minus for the first one, kind of cross product, anyway, some mixed product, and the plus the second one. If you have the dual, somehow you have the same rule as for the complex numbers. For the second component, if you look, it's exactly the same. For the first component is slightly different. But in principle, all the algebra I told you before, with all the rules, how to deal with functions and so on, you could take your library where you implemented maybe when you were a student all the complex numbers, and you just change here and there something, and you get the duals. You don't need to redo everything. Actually, if you think of, there is a minus sign in case of the complex numbers, and this is because when you multiply alpha times beta, you have I squared that is minus 1. In case of the dual numbers, when you multiply alpha times beta, you get a term that is x squared power, and we ignore it. So you can think like, here we multiply by x, but x squared is 0. Okay, so you don't have the term. It's even simpler than what you already know. All of this, there is a branch of mathematics that's somehow studying all this generalization of numbers. It's called hypercomplex numbers. Hypercomplex doesn't mean very complex. Because if you read this, you see, I mean, once you get used, it's very simple. So I think the name is kind of misleading. Anyway, forget about it. This is just a mention that exists a branch of math called hypercomplex numbers. Let's get an example. Okay, finally, after all this theory, we can just try. And you will see that the theory might be scary and maybe you are still not clear for every detail, but when making practice, it's so simple. Let's do it. We take a function, let's say, of three variables, x, y, and z. Okay, so this is a sum of two terms, x times y times z squared, plus sine that is taking as an input x times z. And we want to evaluate the partial derivative of this function in a point, let's say, x equal 2, y equal 3, and z equal 1. If you use the classical methods, the one you learn at school, or symbolic manipulation that is just implementing in the computer, from this function you first find the derivative function. So you start from a function, you determine another function. That is, for example, if you take the partial derivative in x, you are left from the first term with a constant y and z squared. And from the second term, you have the derivative of sine that becomes cosine, and the derivative of the xz, that is going to be z. You substitute the numbers and you get, okay, the result is 3 plus cosine of 2, that is like 2.58. This is what you studied at school. Let's do the same with the duals. With the duals, you don't need to determine any function at all. I mean, you just plug the numbers and you go. Let's see. I put here on the top, let's say, a recap of the rules we will need to do the calculations, just for you. So you take the function and you substitute all the variables x, y, and z by their duals. So x is going to be 2 and 1, okay, because it's the variable. Y is 3, but this is a constant because we are looking at the partial derivative in x. So we take the constant 0, and you are going to substitute z with 3 and 0. The same is for z. Z is a constant, 1, and the second component is 0. Then we write sine, and then inside the sine as an argument, we have the product of what? X that is still 2, 1, and z that is 1, 0. We just make a substitution in the function. We don't compute the derivative, okay? And now we are just to work out this mathematics, okay? So, first step, if you feel confident, try to do yourself, pause the video and so on. But I'm going to tell you, very simple. So, first, we can multiply, for example, the first two duals with the multiplication rule. So, 2, 1 times 3, 0 is going to be, the first component is the product of the two first components. So you have 2 times 3. The second component is going to be the cross product. So you have 2 times 0 plus 1 times 3. Okay, that's the second component. This dual here is the product of the first two. Then you have z squared. Let's take it now. We could use the product rule, but let's use the power rule just to show you a different case. Now k is equal to, and the two components are 1, 0. So the first in the result is going to be the first component squared, okay, 1 squared. And then you have k, that is 2, times b, that is 0, times a, 2 minus 1, so 1. Okay, so you have 2, 0, and 1, they multiply all together. Then you have the sign. The sign, first of all, we need to carry on the multiplication. So again, 2 times 1, this is the first component. The second is the cross product. So 2 times 0 plus 1 times 1. Okay? First step done. Let's simplify a bit. So 2 times 3 is 6. 2 times 0, 0, plus 1 times 3, 3. Okay? So the product of xz is 6, 3. Look, if you were just to multiply the real numbers, you would be 2 times 3 is 6. So the first component is what you're used to. It's the second component that is carrying extra info that will give us the derivative. Then you have the z squared that it was 1 squared, so 1. 2 times 0 times 1, 0. Surprise, surprise, if you take the constant 1 and you square it, you get 1 constant. Then you have the sign. So 2 times 1 is 2, and then 2 times 0, 0, plus 1 times 1, 1. Okay? Surprise, surprise, if you multiply x times constant z equal 1, you just get the same number. Okay? So everything stays there, more or less. Hope you're getting familiar with this kind of calculation. They are very simple. Come on. Now, we can just perform the first multiplication. So, I mean, I don't need to be pedantic. 6 times 1 is 6, and then cross product. 6 times 0, 0, plus 3 times 1, 3. Okay? The sign of a dual, we can use the rule that I already explained. So the first component in the output is the sign of the first component, so sine of 2. The second is going to be the second component 1 times cosine of the first, so cosine of 2. And now we are left with two duals, we just sum them and we get the result. Surprise, surprise, the second component is 3 plus cosine of 2, that is what we wanted. So we obtain the result by just calculating the function. Instead of using a real number, you use duals, boom, you got the result. If you don't remember, the first component, so 6 plus sine of 2, is thus the value of the function if you substitute these values and compute it. Okay, so the first component is the function in 2, 3, 1. The second component is derivative, partial derivative in x in 2, 3, 1. Okay? Now, as an exercise for you, I want you to compute all the partial derivatives in x, y, and z. If you are not able, now I'm going to tell you an hint, but I will prefer you stop the video and try to do paper and pen before you continue. So here, an hint to find the solution. The key part, when you change partial derivatives, is that which of x, y, and z is a variable and which of them is a constant. So when you have the partial derivative in x, you have 2, 1, because x is the variable, 3, 0, because y is a constant, and 1, 0, because z is a constant, and the same inside the sine function. When you want the partial derivative in y, you have x that now is 2, 0, okay, then you have y that is 3, 1, and z that is 1, 0, and the same old in the sine arguments. And for z, of course, x is 2, 0, y is 3, 0, because they are both constants when you look at the derivative in z, and z now is 1, 1. Okay? So you carry on the calculation and you get the result. Well done. We are done. You know everything you need to know about forward differentiation, in automatic differentiation, the forward one. You could implement your own library if you want at this point. You know everything. Okay? Now I want to make 2 extra comments on this. The first observation is that if you look at the results, every time we compute again the function in the point that was not required. We wanted the partial derivatives. We don't want a function. Okay, we get it, but computing it every time is a waste of calculations. This is why many people, let's say, put as a limit to this technology that when you have a function that's taking many variables as an input and in general spitting out a few variables as an output, so you are starting from 3 and going to 1, but you can generalize. In this case, the algorithm is not very efficient. Okay, this is the limit of this algorithm. If you have a function that starting from few variables goes to many, this is super efficient. If you have the way around, it's a limit. One possible solution is to use the reverse accumulation that I will discuss later in this video. But there is another trick that I have found around, and that's somehow to generalize further the duals by introducing some kind of vector duals. Okay, so in this case, you will define an object where the first component is just the function, like you have in the dual, just the value of the function there. The second component is an array containing all the partial derivatives, right? So you can squeeze all the, let's say here I have 3 cases, I squeeze them into one. So you need to take this algebra and, redo each single rule and make sure that you combine all the stuff in a proper way so you don't mess up the result. But if you do this, you might gain some speed, okay, without a need to discover new math. There is a second point that I want to make it, and this is more to make sure you understood everything. What about if I want the second derivative? Try to think about it and then we will go. You feel free to pause the video if you need. The trick or the solution is just to do what you already did. Okay, you define, and let's say instead of a dual, something like with 3 numbers, that is the function, the derivative, the second derivative. Okay, let's say you want to compute the second derivative. If you want to go for the third, you need to add another term. Okay, and then how do you find them? You still use the Taylor expansion. Okay, you needed to generalize our algebra, but keep in mind that the Taylor expansion that now includes a new term. Okay, so now you will make a Taylor expansion including up to x squared, and you redo all I did, including x squared. So, just an example. let's say you want to do the product. Now, you expand both f and g. You want to multiply, let's say, functions f and g. Taking the first three terms, you multiply them. Again, any x to the third power or 4 or fifth, whatever, trash everything. So you keep only up to x squared, right? And you just read the result here. Because each of these terms now, right, you can read it straight. So the product is going to be the product of the finite parts as the first component. You know, here I have the two, let's say, generalized duals, triad, call them as you like. The second component in the result is just the cross product you already used to you know, for the duals. Now you have the x squared term that is containing, let's say, this is a bit more complex stuff. I mean, there are more multiplication. You have f times second derivative in g plus second derivative in f times g plus 2 times the two first derivatives, and you just plug it there. Okay. Remember that now x squared is divided 2, so you know, a bit of... But anyway, in principle, you can just generalize the algebra, and you can take this as an exercise to make sure you understood everything I explained so far. Now we completely change the topic. I mean, you can forget everything I told about duals and forward derivative. I will not use any of those concepts. Actually, you can even, you know, if you just jump in the video right now, it's fine. Okay, we start a completely different algorithm, logic to do the derivatives in an automated way. Okay, and this is basically an algorithm that is based in 3 steps. So first, we evaluate, let's say, the function without really evaluating, but just to study the structure, and we build what is called the computational tree. Okay, so we study the forward evaluation to study the function, and then we go back, because for each step we need to put down the partial derivatives. When we are done, we can finally plug the numbers and do a very quick evaluation of the derivative. Now, let's go step by step. So let's jump into the first step, the forward evaluation. Okay, so let's take the same function we already studied, x, y, z squared plus sine of x, z. We want to evaluate this by breaking down into simple steps. That doesn't matter how many steps we do. We try to make them as simple as possible. Okay, because we want each single calculation to be, you know, the smallest in the sense of amount of calculations, because later will be very useful. Okay, so we introduce some auxiliary variables, okay, to make step by step. So we introduce auxiliary variable, like I call them capital A, capital B, capital C. So A is xy, B is z squared, and C is xz, simple products, okay. So we can rewrite the function as A times B plus sine of C. Now, next step, again, we do the next evaluation, introducing new auxiliary functions to make a small step. So we introduce D, that is the product A times B, and E, that is the sign in C. Okay, so now the function is just D plus E. Finally, we can introduce another variable, we call it F, that is capital F, that is D plus E, right? And we get that the result is equal, the function f in x, y, z is equal to the auxiliary variable f. This is the forward evaluation, okay? Now, some people, like you often see around actually, people draw this as a computational tree where you make all the steps in this way, okay? I'm just telling you, so if you're watching other videos, you will connect this part of my video with the other ones, okay? This is a very well-established part of the, let's say, computational science, even though there is a lot you can optimize there. I'm not going to speak, but just mentioning. Now that we finished the forward evaluation, we go back, okay? So, first, in the backward computation, we start computing the partial derivatives at each auxiliary variable level by nested differentiation. So, the partial derivative of the function f in x, what is it? Is the partial derivative of the function f over the auxiliary variable capital F times the partial derivative of capital F in x. Now we can repeat this by breaking down the auxiliary function f into what? D plus E. So since it's a sum, we are going to get the sum of two terms. Capital F derivative in capital D times capital D derivative in x plus capital F in partial derivative in capital E times partial derivative of capital E in X. We can repeat this, right, to break down D and E in what? In the product AB and the sign of C. So we get another level, okay? The partial derivative in D now is the partial derivative in A times the partial derivative A in X plus the partial derivative D in B times the partial derivative B in X. And the same holds for the second part, where now the partial derivative E in X becomes the partial derivative in C, the partial derivative E over partial C times partial C in X. Okay. Some people, they even further break down because A is itself a function of X and Y. I skip it just because otherwise it will be too messy, but keep in mind that it's going to be like this. Okay. Just we have an recursive somehow breaking down algorithm. Okay, this recursive breaking down algorithm is making us, let's say, helping us to do this backward propagation. But you have to be careful, and this is a point where you might realize that this algorithm can be very heavy, computational memory intense. And why? When you make a recursive call of functions, I mean, think about the factorial. Factorial in n is recursively equal to n times factorial in n minus 1. But this call is going to repeat for n times. So, okay, it's going to be maybe several calls if n is large. But, okay. Now, when you make a recursive call that goes into, the classical example is the binomial. So, the binomial, let's say that I call C computed nk is equal to itself C computed n minus 1, comma, k minus 1, and plus C in n minus 1 plus k, in k. Now, you start from one term, first call you go in 2. If you go second call will be 4. Next call will be 8, 16, 32. After 10 calls, you're going to have 1,000. After 20 calls, you have 1 million. After 30 calls, you have 1 billion. Okay, so you can, if you are not careful the way you implement it, you're gonna make the memory consumption absurd, very large, and at the end crash everything. So even here, if you see, each partial derivative is a function of, let's say, the two variables sometimes they have at the next level. So, can grow very fast. This is somehow a limitation. But if you can do this, you are almost done, okay? Of course, there is an entire branch of, let's say, computational science that is trying to find the best way to build this, forward and backward evaluation, try to optimize everything. I just want to mention there are back propagation algorithms or reverse mode automatic differentiation. Some people, they build some auxiliary tree that is mimic the first, blah, blah. Just be aware that this is an area where people are doing research to try to understand how to make it faster and better and lighter and whatever. Let's skip it. Let's go to the third step for the evaluation. So, we arrive at this point, and now we can finally plug the numbers. If you build this expression on the top right side, you're almost done. Because now the calculations are super simple. So let's take the same point we usually evaluate, right? And we can start evaluating this expression. So, the derivative of capital F in F, if you look at the definition, derivative of capital F in capital F is just 1. So the first term, 1, done. Second term, derivative of F in D. Okay, now capital F is going to be D plus E, so here in green. When you compute the derivative in D, you get 1, done. Partial derivative of capital A, D in capital A. Now, D is equal to A times B, so the derivative will be B. Finally, the derivative of capital A in X is going to be, if you look at the definition, A is X times Y, so it's just Y. Again, derivative in D over B, that is the product A times B, is going to be A this time. And derivative in B in X, since B is Z squared, it's constant, the derivative is 0. Then you have derivative of F in E, so we'll start from here. F D plus E, derivative in D, you are going to end up in 1. Okay. Derivative E in C, let's remind that E is equal to sine of C, so the derivative is going to be cosine of C. And then you have derivative of C in X, C is equal X times Z, so you're left with Z. Okay, so now we can substitute all the numbers that you remember that b is z square, so z is 1 and you have 1 square. Y is 3, that is here. And then you have a, that is x times y, so 2 times 3, we plug it here, okay. And then you have 1 times cosine of c, c is what? X times z, so it's going to be 2 times 1, times z outside of the cosine, that is equal 1. We just perform all this calculation, we get the result you have already seen many times in this video. So the result is 3 plus cosine of 2. We do not calculate, like in the forward case, the value of the function. We just calculated the value of the derivative. Given this, let me give you a bit. So this was an example, because I want you to be able to do paper and pen. Actually, I invite you, you're right, repeat this derivative in, I don't know, y and z. Okay, you already have the results, I hope. And you will be more familiar. But now I'm gonna make, feel free to pause the video, but I'm gonna make now the general case, because I want you to understand where we save computational cost. I told you, so far you need to spend a lot of memory to build this expression. Where is the saving? Let's go. Let's make the same result we already got, but instead of putting x, right, here I have the result in x, let me put it in a generic variable t, where t later on can be x, y, z, or if you have many variables, any one of them. Okay, but now let me keep it as t. Let's see how far we can get without specifying which variable we are looking for. So, first of all, we can substitute all the partial derivatives of the auxiliary functions we had so far, right? So we can gain this expression that is already quite simplified. We still have a generic t. Okay, so up to this point, we can get independently from any variable, okay? We can further, let's say, okay, we multiply by 1, I remove them, and then you say b, what is it, b? b is z squared, so you can just substitute it. Derivative a in t, we explicitly write as derivative xy over t, and so on and so forth. A is xy, b is z squared, and then you have c that is xz, and c that is xz as well. So we have a very somehow simplified expression where we started and we arrived here in a generic way. Now we can take this expression and specify the values and actually evaluate the derivative. So we can plug some numbers, okay, and we get a bit more simplified expression that we can store somewhere in the memory. So z squared is 1, just gone. Xy is 2 times 3, we have 6. And then cosine of xz, that is going to be a cosine of 2. Okay? So when we plug the value of the function, we can do a further simplification, or put some numbers, and this is still general for any variable. Only at the last minute, we specify which t. So if t is equal to x, we just perform the last round of derivatives. Okay? So derivative in x of x times y is just y. Derivative in z is 0, derivative of z squared is 0, and derivative of xz is z. At this point, we plug the number, straight result. But if you have another variable, let's say y, you start from the same expression, and you compute now the derivative in y, so you have x, derivative of z squared is 0, and this derivative is 0 as well. So, we have the result. And if you have z, again, you can just calculate the derivative in z, and you get your result. So, by this example, I hope it's clear how you have to work a bit to build these expressions we have on the top of this page. But when you have them, you can do the 3 derivatives or many, if you have many variables, in a much faster way. So, many people say this, and I agree with them actually, this method, the reverse accumulation, is very convenient when you start from many variables and you go to few. So it's somehow complementary to the forward methodology, even though it's completely different mathematics underlying it. So, to conclude all the discussion, let's say you have you want to implement an artificial intelligence, you have thousands of functions. Of course, you might manually implement all the derivatives, compute them paper and pen, but seriously, do you want to do this? I mean, it's your life, feel free. You might implement the numerical approach I did in the last video. It's simple, intuitive, but very unstable, and quite expensive, computational speaking. You might do the symbolic calculus. This is exact, but generally heavy. You might do the forward automatic differentiation. That is, in general, the best solution when you have a function that starting from few variables goes to many. You can make the reverse automatic differentiation, where generally is the best when you start from many variables and you go into few. Okay? This is not the end of the story, but I think it's quite a good overview. Of course, if you have a very complex situation where you have many variable in input and very variable in output, it's not simple, the answer. There is an entire branch of research that they try to understand what's, somehow some combined technique that, in some cases they use this methodology, in some cases they use that methodology, right? So they try to find what they call optimal Jacobian accumulation, blah, blah. You can transform this stuff into some matrix, and if you see many zeros around, right, when you multiply with many zeros, so that can help you to understand what's the best strategy. I'm not going to speak about it. I hope you at least understood up to this point. I hope you enjoyed this video. And actually I have a request for you. So if you like this video, YouTube cannot really read your mind. Well, partially YouTube can read your mind, but not completely. Maybe one day I will make a video explaining you this part. But anyways, for now, my request is simple. Can you explicitly tell the YouTube algorithm that you like this video by clicking around? You know what to do, come on. If you do it, I will really appreciate it. Thank you a lot and whatever. In the meantime, bye-bye and see you next time.